So what does the rank theorem look like in a specific case? Well, let's take a look at this matrix here. It's a 3 by 4 matrix. It's actually one we've already visited. This matrix is 3 by 4. And the rank theorem, if you remember what we said a moment ago, the rank theorem says that if you add up the rank of a matrix along with the nullity of that same matrix, you're going to get the number of columns of the matrix. So we're expecting, if the rank theorem is to be believed, that the nullity of this matrix A and the rank of this matrix A are going to add up to 4. Well, if you remember, we've already actually computed the nullity. The nullity of A was 2. Let's take a look back at how we got that. Why was the nullity of this matrix A 2? Well, what is the nullity? It's the dimension of the null space. So when we went to go calculate the nullity, the first thing we wanted to do was find a basis for the null space. So the null space, remember, is the set of all solutions to the associated homogeneous system. So we wrote down the augmented matrix of that associated linear system. Then we row reduced it to get the reduced row echelon form version, and then we wrote down the general solution. And in order to do that, we needed to assign a couple of parameters. And the parameters s and t were assigned to the variables x4 and x2. And when we went to go write out our general solution, we then decomposed this into a general linear combination, and we were able to pick off our two basis vectors right here. Okay, so we got a basis consisting of 2 vectors, and that's why the nullity was 2, because the nullity is the dimension of the null space, so you count the basis vectors. It's worth making the observation here that why did we get 2 basis vectors? Why not 3 or 4? Well, once we got to this stage, what did we do? We split this up into the sum of 2 vectors. Why 2 vectors? And why didn't we split it up into a whole bunch of vectors? Well, this was an organizational step. We were splitting this up into the sum of 2 different vectors, one of which had all of the information associated with the parameter t, and the other had all the information associated with the parameter s. So really, you're going to split it up into a number of vectors, and that number is going to happen to be the same number as the number of parameters that you had. So once you got to this stage, you can kind of see what's coming. You can predict that you're probably going to have a nullity of 2 if you only have 2 parameters here, right? But you should still work it out. You still need to work it out and find a basis for the null space to know for sure. And so don't use that as an excuse to skip steps, but it can be used as a good way to check your work and make sure everything's consistent. If you end up having 2 parameters at this stage, you can expect that you're probably going to have a nullity of 2. And if you don't, something went wrong. Okay, but I digress. The point was we already worked out the nullity, and we got 2. So what are you expecting the rank to be? If the nullity and the rank are supposed to add up to 4, the rank had better be 4 as well. Well, let's compute the rank. What is the rank again? It's a dimension of the row space. Okay, how do you get a basis for the row space? Take the non-zero rows of the row echelon form of the matrix. Well, guess what? I got good news. This matrix is already in row echelon form. So we don't need to do any row reduction. We can just take the non-zero rows, which is row 1 and row 2. So now you can see why this is going to work, right? But let's work out the details and do everything formally. So let's write out, first of all, a basis for the row space. So our first basis vector is 2, negative 3, 4, and 2. And our second basis vector is 0, 0, negative 1, 7. So that is a basis for the row space. And that tells you then that the rank of A, which is by definition the dimension of the row space of A, is equal to 2, because the number of vectors in the basis is equal to 2. So, well, then that confirms the rank theorem in this case, right? So let's add one line over here. The rank of A plus the nullity of A, oops, I forgot the y, is, well, it's 2 plus 2, which is equal to 4. And that matches up with what we got up there, right? We had 4 was the number of columns of A, and the rank and the nullity of A both add up to 4. So that's always going to happen. That's the rank theorem in action. Okay, why is that true, by the way? Why did that work? Why does the rank and the nullity add up to the number of columns of the matrix? And the reason, I won't go through a formal proof, but we can still informally kind of look at and see why this is not surprising at the very least, right? How do you know how many parameters you're going to have, right? Because remember, the number of parameters is very closely linked with the nullity. In fact, the number of parameters is the nullity. Why do we only have 2 parameters? Well, when you look at the reduced row echelon form of the augmented matrix at this stage, you look at which columns don't have leading ones. And the columns that don't have leading ones, those are going to be the variables that get assigned parameters. Well, what's left? The columns that do have leading ones. So each of those leading ones corresponds to a non-zero row of the row echelon form of the augmented matrix we started with, right? So for each of the columns that have a leading one, the pivot columns, they also correspond to rows that are going to be used. I should be circling this part only now. They correspond to rows that are going to appear as basis vectors for your row space. So think about it this way. You can go through the columns one by one. Every time you see a column that has no leading one, you can add 1 to the nullity. And every time you see a column that does have a leading one, you can add 1 to the rank. And by the time you're done, how many times will you have added 1 to either of those 2 quantities? Well, however many columns you have, right? So that's why the nullity and the rank add up to the number of columns. It's not, when you think about it the right way, it's really the only thing that could happen, right? So it's nothing magical. It's just based on the way the terminology was defined. But this is what it looks like in practice. Okay, so what do you see that's left here? You see the invertible matrix theorem. And if I just circle this part, this is what we've already talked about this in, I think it was section 2.3, I think, right? Or 2.2, I can't remember, but it was one of those sections. We've already talked about the invertible matrix theorem. It's a whole bunch of statements that are all true under the exact same circumstances, meaning they're either all true or they're all false, right? And all you start with is the assumption that you have a square matrix A, and then you can go through, you can treat all of these statements as different ways of saying the exact same thing. So I'm not going to go through these ones in detail because we've already went through them. You can go back to that section again and go through those again with me slowly if you like. But we're going to focus on statements K, L, M, N, and O. And really, there's not going to be really anything new here. It's just, these are just different ways of saying the same thing again, right? We have the advantage now, we have more terminology that we can make use of, so we can actually make some of these statements more condensed and concise now. So let's take a look at the first one. So statement K. The columns of A form a basis for Rn. Why is that, by the way? Well, if you look at statement F and statement G, what does statement F say? And let's think about it this way. If your matrix A is invertible, then you can also make every other statement in this list, right? So if A is invertible, then this statement F says that the columns of A are linearly independent. But statement G says that the columns of A span or give you a spanning set for Rn. So what does that mean if you put those two statements together? Well, then you have a linearly independent spanning set for Rn, which means you have a basis for Rn. That's exactly what a basis is. So this is just essentially putting statements F and G together. That will give you statement K. Okay, and now statement L just says that the column space of A is equal to Rn. Well, that's nothing new. That's just a reformulation of statement G, right? Because the column space of A is exactly, by definition, the span of the columns of A. Remember A1, A2 up to AN, those just denote the columns of the matrix A. So statement L is nothing new. That's just saying, repeating statement G, just using, now that we know what the column space means, we can say statement G more concisely. Okay, so statement M says that the row space of A is equal to what? Also Rn. Now, why is that the case? Why would the rows also span Rn? Remember, because if I say the row space is equal to Rn, I'm saying that the span of the rows of A is equal to Rn. Let's look at why that's true. Let's write out a bit of like a kind of a diagram that links these statements together. So if I start with the I'm going to abbreviate this just to keep it short. If I just say A is invertible, so I'll just say A invertible, that is equivalent to the column space of A is equal to Rn. How am I getting that? I'm just linking statement A and statement L. That's all we're doing, okay? Now, if you think back, there was earlier in this chapter, we've made a remark that says that a matrix A is invertible exactly when its transpose is invertible. So if A is invertible, so is its transpose. In fact, the inverse of the transpose is just the transpose of the inverse. That was a formula for the inverse of a transpose. Well, what does that tell you? What else does that tell you then? Well, if A transpose is invertible, that means the column space of A transpose has got to also be Rn. But remember, the column space of A transpose is equivalent to the row space of A. So we can say this is equivalent to saying that the row space of A is Rn. Okay, now I actually have to beg your pardon here. As I was getting down to the bottom of this list, I realized I missed one. And I can't skip it because it throws off the logic, and it's important because this one leads into statement N. So the simplest thing I think is just to add it to the bottom, and then what I'll do is just do them out of order. Okay, so statement P, and this let's actually start with statement M, and we can build statement P just by thinking about what statement M says. So statement M says that the row space of A is equal to Rn. Well, take the dimension of both sides of that equation. So if you take the dimension of the left-hand side, what do you get? You get the dimension of the row space. Well, the dimension of the row space is the definition of the rank of A, right? And if I take the dimension of the right-hand side, I'm going to get the dimension of Rn. And if you remember, and if you don't remember, scroll up, flip back a couple of pages, but the dimension of Rn is actually n. So on the right-hand side, we're going to get n. So that tells you that the rank of A is equal to n. But the rank theorem, now let's apply the rank theorem to statement P. If the rank theorem is n, remember the rank theorem says that the rank of A and the nullity of A have to add up to n. Well, that tells you what the nullity is. If the rank of A is already n, then the nullity must be 0. So we can say that the nullity of A is equal to 0. Well, the nullity of A is the dimension of the null space of A. You're saying that the null space of A is zero-dimensional. It's a zero-dimensional subspace. Well, there is only one zero-dimensional subspace. It's the only subspace that doesn't have a basis, and that is the trivial subspace. That's the subspace consisting of only the zero vector. So the null space is the trivial subspace. Okay, so now you have more frames of, well, not frame, let me say, you have more points of view to add to your toolkit when you're thinking about invertibility. Remember, all of these statements are equivalent to saying that the matrix A is invertible. These statements aren't always true, but they are true if the matrix A is invertible. And if any of these statements are true, then you know that the matrix is invertible as well. The logic works both ways. That's the beauty of this theorem.